Today we'll be talking about model-based RL for multitask learning. And so far we've talked, all the RL that we've talked about is model-free. And so we'll be talking about a different class of approaches that you leverage models. So some logistics. We sent out the mid-quarter survey. This is to kind of supplement the high-resolution feedback that we've already been doing. But we'd really value your feedback. The feedback that we've used in previous quarters kind of helped us improve the course. It's one of the reasons why we're using PyTorch for the assignments this quarter, among a number of other things. Also, homework 3 is out, and it's due Wednesday next week. And then the optional homework 4 will also go out next week on Wednesday. Great. So today, I'll briefly recap goal-conditioned RL and relabeling. This is the topic of homework 3. And so we'll just do a quick recap of that to get on the same page, and then we'll transition into model-based RL. And we'll talk about how model-based RL can be used for multitask learning. And then we'll also be talking about model-based RL when you have image observations or other like high-dimensional inputs, because that's introduces an additional challenge in the model-based setting. And then the goals of the lecture will be to understand how to use and implement some simple model-based RL algorithms, to understand how model-based RL can be used for multitask reinforcement learning, and some of the challenges and strategies for performing model-based RL in high-dimensional spaces. Cool. So to recap the lecture on Wednesday last week and Monday this week, we introduced kind of model-free reinforcement learning methods, such as policy gradients and Q-learning. And we saw this sort of kind of anatomy of an algorithm where you collect data by, for example, running your policy. Then you fit some form of model to estimate return, and then you use that to improve your policy. And we saw a couple different cases of actually instantiating this kind of framework. So for example, you could try to estimate the return directly by just summing your rewards, or you could actually fit a critic Q function to try to estimate your expected return from your future state, from your current state. And then once you have this estimate of your future return, you can use that to either update your policy using a policy gradient directly, or by taking the actions that will maximize your Q value. Now, in this lecture, we're going to be focusing on model-based RL methods, which will actually incorporate a different kind of model in order to improve the policy. Previously, we also talked about what a reinforcement learning task is. A task essentially corresponds to a Markov decision process, which has a state space, an action space, initial state, distribution, dynamics, and reward. And different aspects of this problem can essentially correspond to different tasks. Some tasks might share a lot of aspects of these and only have one thing varying. Alternatively, we could view this as having a task identifier be part of the state, where S bar is your original state space and Zi is your task identifier. In this case, your policy, you can view your policy as essentially conditioning on your task identifier. And likewise, also your key function conditioning on the task identifier. Zi could be a number of different things. It could be a one-hot task ID. It could be a natural language description of the task. It could also be a desired goal state, like a particular state that you want to be able to reach. And in this case, this is what's referred to as goal-conditioned RL, which is a special case of multitask reinforcement learning. Great. So we also looked at this example where we want to hit a puck into a goal, or we either want to hit it into a goal or pass it to our teammate. So task 1 is passing, and task 2 is shooting goals. And if you accidentally perform a good pass when you're trying to shoot a goal, then you can actually store that experience as normal, but also pretend that that was actually what you're trying to do, and relabel that experience with the task identifier of task 1. I think that's a typo. Relabel it with task 1 and store it in your buffer. So this is referred to as data sharing in multitask RL. and also known as hindsight relabeling, where we're going to be kind of in hindsight relabeling what the task that we were actually doing in order to improve learning for these different tasks, or hindsight experience replay. Great, so we saw this algorithm, which you're going to be implementing in homework 3, where you collect data using some policy, then you store that data in your replay buffer. And then when you want to perform hindsight relabeling, you take your experience in DK and you relabel the last state. When you choose what the goal is or what the task identifier is for that particular transition or for that particular trajectory, you will set the goal to be the last state in that trajectory. Great, and so you can see that right here where you have your experience and then your goal is the third element of that tuple, which is storing ST instead of the original goal that you were trying to accomplish. Then you'll store that relabeled data in the replay buffer and then update your policy using the data that you have so far. And you'll iterate and so forth. There's also other relabeling strategies rather than just relabeling the goal as the last state. You could also really choose, for example, any state in the trajectory, or you could pick a random state as well. And in your homework, you'll explore these different strategies. Okay, and then the result of this procedure is that this can help with exploration because if we incidentally collected data that's useful for other tasks, we are sharing that data across the tasks. So you don't have to explore for every single task independently. Cool. So that was a brief recap of goal-conditioned RL. Any questions on that before we get to model-based RL? Okay. So in model-based reinforcement learning, really the main idea here is to learn a model of the environment. And what I mean by that is we're actually going to try to learn what the next state is given the current state in action. We're going to actually learn how to predict the future, basically. And this can be useful because if you can learn a model like this, it often leads to better data efficiency because then you can query that model rather than the true environment. And you can also reuse this model across different tasks. And so at a high level, the way that this works is you try to estimate the distribution of the next state given the current state in action with some function f. And then once you have this model, you use it to plan actions to take. That's kind of the high level gist of it, how it works. We try to fit a model, we try to learn how to predict the future, and then we use that model when choosing actions. It's also worth mentioning that instead of planning actions, you could also use it to fit a policy. In this lecture, we're going to be focusing on using it for planning. But if you're interested in learning more about how to optimize policies with it, I'm happy to discuss that in office hours or something. And now one of the things that's nice about this is how do you go about learning this model? You can learn it just with supervised learning, where, for example, you're trying to minimize something like the mean squared error between your model's predictions and the true next state. And supervised learning is pretty nice. You know how to do it pretty well. Okay, cool. And like I mentioned, you can also use it to optimize a policy. So what does this have to do with multitask reinforcement learning? One thing that's really nice about model-based RL is that there is a special class of multitask RL problems that it is actually quite amenable to, which is that in the general case, we consider tasks that look like this. But in many situations, only the reward function is going to be varying across tasks, and you'll have the same state space, action space, and dynamics. And really today we're going to be focusing on this special case where each task corresponds to something like this, where you notice that only the reward is indexed by I, and all of the other aspects of the task are shared across all of the tasks. So we can think about a few examples. So maybe in robotics, the laws of physics are constant across different parts of the world, but you might want your robot to perform different objectives, like doing laundry for you, cooking for you, that sort of stuff. And so in this case, these different tasks correspond to this special case where only the reward is changing and everything else is constant. Another example is maybe we want a kind of virtual assistant or some form of dialogue system where the user and the language that it's speaking in are constant across the tasks, but you have different objectives. So maybe in some cases you want it to order food for you, maybe you want to provide emotional support. In this case, also the dynamics and the state space and everything are the same, but the reward function, like ultimately what you want it to accomplish for you, is different. Yeah.
What if we have two different robots, then that would not be the case, right? So.
Yeah, so if your different tasks correspond to different robots, if those robots have different embodiments or something like that, then these things would vary across tasks, yeah. Cool, and then in autonomous driving, another example is that usually the rules of the road are relatively constant if you're in the same country, for example. But different preferences, users have different preferences. Some people maybe want you to drive fast, some people might want you to drive smoothly. Maybe you also want to get to different destinations. And so in this case, again, generally the dynamics are the same, assuming that it's the same car as well. But what's differing is the objective that you're trying to accomplish. So one thing that you can notice here is that in this case, where this is our sets of tasks look like this, the model is the same across all the tasks. And so estimating the model is actually a single task learning problem. And where the multitask part comes in is actually how you use that model to plan actions. And this is pretty nice because learning the model, or generally learning about an MDP, can be challenging. And if it's a single task learning problem, then it's going to be easier than a multitask problem. So we can fit a single model for all of the tasks and then just plan to accomplish different tasks using that single model. Okay, so how do we actually use a model to plan? The gist of the approach that we'll consider is to optimize your actions using the model. And we have this objective right here, which is to maximize our sum of rewards. And we're performing this maximization over our sequence of actions. So we're essentially trying to find a course of action that will lead to maximal reward. And this optimization is referred to more colloquially as planning, in the sense that you're essentially planning what you want to do in order to accomplish an objective. Yeah?
We're trying to estimate the probability P, but is the reward function known as well beforehand, or are we unsure about that as well?
Yeah, it's a great question. So the question was, do we know the form of the reward function? We're learning the dynamics. Do we know the form of the reward function? In some cases, yes. In some cases, no. I'll talk about the two cases after we go through the process. You can assume that we know, in all these cases, you can assume that we know the functional form of R, that we can essentially evaluate R given a state in action. But we might have known it or we might have learned it. Yeah?
So why is state planning? Do you mean open loop planning or closed loop?
Yeah, great question. So do I mean open loop planning or closed loop planning? We're going to start with open loop planning, and then we'll talk about closed loop planning after that. And it's a pretty important distinction, and it'll come up later. Cool. So how do we actually go about optimizing this objective? So we have our model, and you can think of, you can essentially like roll out your model, kind of apply it iteratively from your current state to, given your actions, to kind of predict what the future will look like in a computation graph like this. And then we can also measure the reward given the state in action at each time step. And so if we want to optimize the actions that maximize rewards and we know our model, then what we can do is we can essentially backpropagate from the rewards into the actions. And essentially run this computation graph, compute the gradients of the rewards with respect to the actions using your dynamics model. And so note here that we're going to be doing gradient descent, but instead of doing gradient descent on some parameters, we're going to be doing gradient descent on our actions. And so explicitly what this will look like is, first we're going to run some policy to collect some data. This could be a random policy, for example. Then we'll fit a model using the data from this policy. This is just done with supervised learning. And then we'll backpropagate from the reward through the model into the actions to choose actions. And this last step here will essentially pick an initial set of actions that are sampled randomly, and then run gradient descent by iteratively computing the gradient of the action, of the reward with respect to the action, applying that gradient to the action, and then repeating. Yeah?
Like computing the expected value and then using like the dynamic programming framework. Because you have all of that.
Yeah, so because we have a model, if the model is accurate, we can actually leverage leverage that functional form of that model to backpropagate through it. And this is going to be better than something like Q-learning if your model is accurate, because the model is not only going to tell you what the future will look like, it's also going to tell you like the gradients of your action, how your action affects your state, basically. Yeah.
And what if the actions were discrete, or like categorical or something like that, rather than continuous?
Yeah, so the question is, what if your actions are discrete rather than continuous? In that case, I probably wouldn't use backpropagation, and on the approach 1B, we'll see something that would work for discrete actions. You could also consider trying to optimize with respect to some sampling distribution and kind of use a gradient estimator to differentiate through the sampling process from that discrete distribution. But in general, that sort of gradient estimation is prone to errors. Yeah.
So like, if you do this process, like under step 3, wouldn't you only get, so you would only get gradients with respect to the actions you pick in the data set, right? So like, would that just tell you how, like, what would have been better actions within that data set?
Yeah, so the question is, does this only give you actions with, does this only give you gradients with respect to actions in your data set? And the answer is no, you can actually get gradients for actions that aren't in your data set. And essentially what this third process corresponds to is first you pick some initial A1 to H. This could be like in neural networks, you randomly initialize your parameters, you're going to randomly initialize your action sequence. And then you can basically compute the gradient of your sum of rewards with respect to this action sequence. And the way that you can compute this is basically with the chain rule, where you use dr, d. I'm going to assume that the reward only depends on state for now. Dr, ds, and then ds. I guess this is technically dr, d, like all of the time steps, s1 to h. And then you're going to take the gradient of this with respect to your actions, 1 to h. And this is going to, this gradient is what's going to be using your dynamics model by essentially backpropagating through that model. This does assume that your model, the model that you learn, is differentiable. Fortunately, things like neural networks, you can differentiate through them. And so you're going to be differentiating into the inputs of the model, not into the parameters of the model. And then you'll, for completeness, you'll then apply this gradient to update. So it'll be 1 minus the gradient, something like that. And you'll have some learning rate. Yeah?
If you wanted to apply another gradient step, would you have to, then you'd have to re-roll out these actions, or?
Yeah, so then when you want to then kind of iterate this process, you will need to then run these actions through your model again and backpropagate into them again. And the reason why this works is that you can evaluate your model on lots of different action sequences, not just the ones in the data. Yeah?
I feel like this grad error true loss in stat 2 doesn't work in some cases, like if you have too much irrelevant information in state, and the script error too much will pay much attention to those irrelevant information.
Yeah, so the question is, when you're fitting your model, if there's a lot of dimensions of the state that have irrelevant information that's irrelevant to the reward, will the squared, like the L2 loss, will that cause problems essentially? And the model will actually have to model everything in the state, and if there's only a very tiny part of the state that is relevant towards the reward, then this approach might struggle if it doesn't model that part of the state well. And so that is one of the downsides of model-based approaches, is that there is this mismatch between the goal of fitting a model and the goal of kind of fitting the return, especially if there's large parts of the state that aren't relevant to the return. Cool. So gradient-based optimization is the first way that we can go about optimizing for our actions, for going about planning, essentially. The second way that we can go about this is with a sampling-based optimization. And we're going to be still trying to optimize the same objective, but instead of using gradients, we're going to use a gradient-free operation or optimization that tries to essentially just sample actions and choose the actions that perform the best. So the algorithm itself will look basically the same as before. We're going to run some policy, use a model to fit the dynamics from that data, and then we're going to perform a sampling-based optimization to choose actions. What do different sampling-based optimizations look like? The dumbest approach is to basically just randomly sample and pick the best one. So what this looks like is we'll denote our action sequence with capital A, just for brevity. And in kind of really the simplest approach that we could do here is we guess and check. So we'll sample a bunch of different action sequences, like maybe 1,000 or 10,000 or something, from some distribution, like a uniform distribution. And then we'll just choose the action sequence that maximizes reward. This is maybe not the smartest way to optimize the objective, but if you actually parallelize the sampling process and the evaluation process, it can actually be super fast, which is nice. It also works with discrete actions. Of course, this also has limitations, which is that if your sampling distribution is very broad or isn't very good, then the action sequence that you'll get also won't be very good. Yeah.
Your application version 1 doesn't seem as though like across multiple steps anything new is going to happen. Like you're just doing the outback of the same thing again and again.
So this is the kind of the optimization for choosing actions with respect to our model, and we're going to be learning the model, and then after we learn the model, we're going to be using this to plan actions with respect to that model. Yeah, the model is still optimized with gradient descent. Now this is kind of not the smartest approach, and it's referred to as random shooting because you are kind of essentially shooting out different action sequences at random and trying to pick the one that works the best. Can we improve this distribution? One version of this algorithm that is slightly better is instead of just taking a single distribution and sampling from it, is we could actually iteratively improve that distribution. And this is what's known as the cross-entropy method. So we first start by sampling action sequences from some distribution, P. This could initially be the uniform distribution. Then we evaluate the sum of rewards for each of those action sequences. We see how well they did. And then what we'll do is we'll pick the action sequences that had the best reward, and we'll refit a distribution to those best action sequences. And then we can essentially repeat this process and then resample from that improved distribution, basically from the distribution that did the best, and then kind of iteratively refine our distribution that we're sampling from. And kind of in terms of some of the details, I think that this process is fairly straightforward. You evaluate each of your action sequences and you pick the ones that are the best or the elites. In terms of fitting a distribution to this, you could fit a Gaussian distribution to it. You could fit a mixture of Gaussians to those action sequences or something else. This is probably the most complicated step, but once you do this, then you just resample from that distribution and repeat. There are also more advanced methods for sampling-based optimization. There's what's called kind of evolutionary methods and so a method called CMAES. But it turns out that actually, in a lot of cases, these two approaches aren't actually as bad as you might think. Yeah?
Is like we're refitting to like the samples that are weighted, I guess like the most off of like this initial like random sample, so you kind of get to like a local optimum due to that, or like how do you kind of like maintain good probability off of like cases that you don't get in like the initial distribution?
Yeah, so you do need to get good coverage from your initial distribution, and the question was like, do you get stuck in a local optimum potentially? If you have good coverage in this initial distribution and your optimization landscape is somewhat smooth, then it shouldn't get stuck. But if, for example, say you like sample from this distribution and like right here is like really good, but everything around that is not very good, and you like draw some samples that don't include that region right there, then you are going to miss this because maybe there's a spot over here that's like a little bit better. And in that case, you will not hit the global optimum because you have this pretty non-smooth landscape. If you have a smoother landscape where like this part is clearly better than other parts of the landscape, then it'll be easier for it to optimize. That's also true for gradient-based methods as well. Gradient-based methods they are a local optimization, and if the gradient, for example, points them towards an optimum that isn't as good as another one, then they'll also get stuck. So to recap, the way that we kind of iteratively resample is we sample at random to start, and then we pick some subset of those samples that are the best. We refit a distribution to those samples, and then resample from that distribution. Cool. So for sampling-based optimization, one of the benefits of this is that it's pretty fast, especially if you parallelize things. The only thing that's iterative is the different iterations of the cross-entropy method. Whereas gradient descent is fully sequential and you can't parallelize it easily. It's also super simple, so it's pretty easy to implement. And you don't need to worry as much about the initialization, for example. The downside is that it doesn't scale to high dimensions. Fortunately, action sequences are usually much lower dimensional than, say, neural network parameters. So this is one reason why we would use this kind of optimization for action sequences, and we definitely wouldn't use it for neural network parameters, although actually some people have found it to sometimes work for neural network parameters. This includes, in terms of dimensionality, this includes both the horizon and your action dimensionality. And that's because when you do this optimization, you're optimizing over the entire sequence of actions and not just the first action, for example. And it is important to optimize over the entire sequence so that you actually consider long-term outcomes. Cool. So in terms of the algorithm, the kind of jumping back up, we're again going to be kind of collecting some data, fitting a model, and then improving or optimizing for action sequences with respect to that model. For example, using random shooting or cross-entropy method, or using a gradient-based optimization. Cool. So that was essentially version 1 and really one of the basics of model-based RL. Now, how can this approach fail? So say, for example, you are here and you want to get up to be as high as possible. You want to get to the kind of top of You want to be higher so that you can see further or something like that. You're first going to run some policy, and you'll collect data that looks maybe something like this, because it's some random policy. Then you'll learn a model to fit this data that tells you what, essentially what will happen if you go in certain directions. And one thing that you might learn from this data is that if you go towards the right, then you can go higher. Because in this kind of region where you collected data, you always saw that if you went right, you got to a higher elevation. And then now you're going to optimize for actions or plan actions so that you maximize reward. And so if you want to go higher, you'll learn that you should go to the right. And then now one thing you might notice here is that if you do that, then you'll kind of keep on going right and fall off the cliff. Now, what went wrong here? So the issue here is that there's this data distribution mismatch between the data that you fit the model on and the data that you're using the model on, that you're evaluating the model on. And essentially the distribution from the initial policy on the left is different from the state distribution that you're actually evaluating your final policy on. And your model didn't see any data of falling off the cliff, and so it doesn't know how to avoid falling off the cliff. Cool. So a thought exercise for all of you. How might you go about alleviating this issue? Yeah?
Use randomly intentionally try to explore as much as possible.
Yeah, so the one thing that you could do is in your initial policy, try to explore as much as possible so that you can see a much broader distribution and so that you can cover more. That's a good idea. Yeah?
Constrain your policy by them from not being too far from policy by 0 and explore way too much.
Yeah, so when you optimize for actions, you could optimize not just for maximizing reward, but also staying close to your initial policy. Other thoughts? Yeah?
One question.
Sorry, can you repeat that?
With many iterations recognize the true data.
With many iterations, would you recognize the true data distribution? Yeah, so I think that you could essentially view this as a suggestion for how to alleviate the problem, which is that one thing that you could do is kind of collect data using your model and then add that data to your buffer of data and refit your model using the data that you collected by planning. So that's a third thing that we can do. Any other ideas? Okay, so those are good suggestions. The first suggestion was collect more diverse data at the beginning. The second was to try to stay close to your initial policy. And then the third was to recollect data. I'm going to kind of outline the last one, which is that when you kind of start planning with your model, you can then execute those planned actions and append that data to your data set and then refit your model with that data set. And this is a nice approach because it means that you can explicitly, in a very targeted way, try to explore to regions where you think that there might be reward because you're planning to try to reach those regions, and learn a good model in the parts of the state space where you think that there might be good reward. Cool. Okay, so then if you do this, if you execute your planned actions, you'll collect data that looks like this. So you'll learn what it's like to fall off cliffs, and then you'll learn to kind of eventually go to the top and then stop, because your model will learn that if you keep on going from that point, you will no longer go higher. Yeah.
So, could you go back one slide, please?
Yeah.
So if you do this, then you're sending more damage to your data set for the actions that you think are good. So does this kind of give us a bad estimate of the other actions, other state action features that
You mean, does it give you a bad estimate for the kind of initial data, or?
Well, what I mean is that in step 4, you're appending actions to your data set that you think have good based on step 3. So you have less data for actions that are good.
Yeah, great question. So the question is, doesn't this mean that we're going to have less data for parts of the state space or parts of the kind of action distributions that are less good? And the short answer is yes. So we'll have less data in those regions. The good news is that even though you'll have less data and your model will be less accurate in those regions, if it then thinks that some of those action sequences are good, because like erroneously thinks that they're going to be good, then it will eventually kind of optimize for reward, pick those actions, and then collect data. And it's essentially going to be self-correcting, where whenever it erroneously thinks something is good, then it will collect data in that region and then ultimately learn that it's not good. And if there's any parts of the state space that you don't have a lot of data in but think are bad, then it will choose not to visit those parts of the state space. Cool. So this is kind of the kind of complete version 1 of model-based RL, where you fit a model to some data, you plan using that model, and then you add that data to your buffer. Now, the last version that I'd like to talk about is trying to do a little bit better than this. And this is getting back to the question of open loop versus closed loop. So one of the things that you might have noticed is that right now we are planning a sequence of actions and then executing those actions in the environment. And what this ends up looking like is if you have your agent and you have your world, then what it's going to do is it's going to kind of execute the actions that it optimized, and in order to kind of try to accomplish the task. And this is what's referred to as open loop. And then there's a kind of alternative paradigm where you're actually going to try to close this loop, where at each time step, instead of just passing in or kind of taking the sequence of actions and running them, you're going to take one action and then see what the next state is, and then use that next state to determine your next action. And so this is what's referred to as closed loop, hopefully for reasons that are clear, because we see a loop there. Now, does anyone have thoughts on when open loop might be a bad idea? Yeah.
If my environment is stochastic.
Yeah, so if your environment is stochastic, then this open loop version is going to be suboptimal, most likely. And the reason for that is that if you don't know what your next state is, then if there's basically stochasticity in your dynamics, then if you base your actions on your most recent state, then you'll be able to account for what happens in the stochasticity in the dynamics. Whereas in this case, you don't have any way to account for the fact that like st plus 1 or st plus 2 might be different from kind of the average case. Cool. So then does anyone have thoughts on how we might accomplish this closed loop approach in model-based RL? Yeah?
So in both cases of the open loop, we're still looking at like 10 action steps, defining steps actions for each one. It's except we're now in closed loop because we're just applying one action, saying what the next state is, and redoing that process.
Yeah, exactly. So in both cases, we are going to be trying to look ahead and like predict what's going to happen in the future. The key difference is that if we're uncertain about what's going to happen, then we need to, in this case, we need a plan with respect to like that uncertainty. We need to plan under lots of different possible circumstances that might happen, and then just kind of execute an action sequence that seems reasonable with according to those predictions, where in this case we essentially get a look at the next state and kind of decide what actions to take, again, based off of the state that we saw. Yeah?
In one of my other classes, we do the same thing. And, so you have, it's sort of like a tracking approach where you have the state sequence that you think you're going to get based on that action sequence, and then the state sequence that you actually do. And then when you try to like match those, try to stay close to the actions that make that state sequence that you actually take closer to the one that you want.
Yeah, so that's an interesting idea. So one thing that you could essentially try to do, if I'm understanding correctly, is to try to basically try to choose actions so that you are staying in a part of the space that is fairly predictable. And so if you're trying to essentially match the trajectories between what you think and what actually happens, then you're essentially going to try to stay in parts of the space where the dynamics are more deterministic. And in that case, actually, an open loop plan might work a lot better because it's going to be, if there are parts of the state space that are more deterministic, then you can try to solve the task by staying in those parts of the state space. Is that kind of what you were thinking?
Yeah.
Cool. So that's actually a pretty cool thing. It's not actually that common to do that because estimating how deterministic things are is a little bit difficult, but there are some more advanced techniques that do something like that that are pretty cool. And then in terms of like so that something like that would still be somewhat open loop. In terms of how we could kind of move towards the second paradigm here, what we can do is instead of planning a sequence of actions at the first time step and rolling them out, what we can do is we can plan at the first time step, optimize for our sequence of actions, take only the first action in that sequence, and then observe what the next state is. And then once you observe the next state, you can replan and rerun your optimization to, again, pick an action sequence from that new state. And this sort of replanning approach can essentially account for the dynamics in the environment, especially stochastic dynamics. It may be a little bit expensive because you're going to be running this planning step at every single time step potentially. But one thing that you could do is you could potentially warm start the optimization from the plan that you had at the previous time step. And so in terms of how this works, this is essentially what's referred to as model predictive control, or MPC, which is maybe a bit of a fancy name. But essentially what it is you run some initial policy, you learn a model from that policy, you use that model to optimize for your sequence of actions. Then instead of executing all of the actions, you execute only the first planned action and observe the resulting state. And then you kind of go back to optimizing your action sequence from there. We'll also kind of append this to the data set, but we're going to have essentially these two loops. One loop is this inner loop is the closed loop process where we're going to be kind of replanning at every single time step. And this outer loop is going to be the process of adding data to your buffer and refitting your model. Yeah.
And one quick question. So our F-fitted model, isn't it going to be stochastic then too? So wouldn't we need to then do a stochastic look ahead when we solve the equations and when we...
Yeah, so the question is, shouldn't our model F also be stochastic? So if your dynamics are stochastic, you should also try to fit a model that's stochastic. In the slides, for simplicity, I was denoting it as kind of just using mean squared error in a deterministic model. One of the things that's cool about the sampling-based approach is even if you have a stochastic model, you don't have to change anything about this optimization. With gradient-based approaches, you could also choose to, I guess it depends on how you implement your model, but it's not too difficult to optimize through that, depending on some of the details. And in that case, you'd be fitting a model F that is like modeling the distribution over S prime rather than just outputting a deterministic estimate for S prime. And then the way this works is if you kind of accidentally make a mistake at one time step and notice that you made that mistake, then you can actually essentially correct for that error that you made, or correct for some aspect of the dynamics that were unpredictable. Cool. So this can correct for model errors. It is more compute intensive because we are trying to run things, run this sort of planning at every single time step. In particular, it's compute intensive at test time rather than at training time. But there are ways to try to like warm start the optimization to alleviate that challenge. Okay, so what does this all have to do with multitask RL? Like I mentioned before, there are two cases with respect to the reward function. In one case, maybe you know the form of the reward function exactly. So maybe you can observe the positions of objects, and your goal is to like get the object position to be in a certain position. Then what you could do is learn a single model and then plan with respect to each of your reward functions at test time. And so at test time, if you're told that you should do task 1, then you can plan with respect to the reward for task 1, and likewise for the other tasks. So as an example for this, RI might correspond to trying to accomplish some different pencil trajectories by essentially writing different characters. And what this approach is doing is it's running planning with respect to a model that it learned to try to write these different trajectories and write these different digits. So for example, the second one is a 7, the third one is a 4. I think the last one might be a 5. RI corresponds to these different trajectories, and we can just, once we have our model, we can plan to accomplish all of these different trajectories at test time. As another example, RI could also correspond to different trajectories or positions of a ball held in the hand. And so, for example, here you see these little red dots that are spinning, and this is showing the desired trajectory of the two balls in the hand. And it's running planning with respect to a learned model in order to spin the balls in its hand. And also, you can give it, for example, different goal positions of a single ball, and it can also figure out how to move its hand in a way that will hit that target position. And here's another example. I think in this case, it's going clockwise instead of counterclockwise. Cool. Then one last caveat that I'll mention is that in the multitask scenario, if you are iteratively collecting data, the reward is going to change what data you collect. And so you will want to, during training, you're going to want to have different reward functions in order to cover the distribution of tasks in terms of the data that you collect. Cool. And then one other thing that's pretty cool is model-based RL tends to be fairly sample efficient. And this means that you can actually run the same approach on a real robot. And this is a 5-fingered shadow hand that is kind of twirling these two balls with exactly the approach that we talked about before, where it's learning a dynamics model from a couple hours of data on the robot, and then running planning with respect to this trajectory-like goal at test time. Cool. So that was the case where we knew the reward function as a function of the state. And in particular, we knew the positions of the objects, and then we just measured the reward function as like the distance or the negative distance between the object position and the goal position. In other cases, we might not know the reward function directly. And there's a few different ways that we can do this. We can try to learn a reward function with supervised learning and use that learned reward function in addition to the learned model in order to plan. Another thing that we could do is we could also meta-learn a reward function, where we're given a few examples of success and failure for a reward function, and we want to kind of adapt our reward function based on that data. And so an example of doing this is you can give it, if you do some sort of meta-learning approach for learning a success classifier, you can give it some positive examples of success. So in this case, the goal is to put the pencil case behind the notebook. And the robot is just looking at the images here. The state space is just images. And we'll use this to acquire a reward function for this particular task, where it should assign kind of a positive value for when it's behind the notebook and a negative value when it's not. And then once we have this binary reward function, we can use it for planning. So we'll learn a model and then plan with respect to that model to try to accomplish the goal and push the pencil case to be behind the notebook. Cool. And this allows you to both solve multitask RL as well as the meta RL problem statement, depending on the kind of supervision that you have. Cool. Any questions on this before we move on? Cool. So next we'll talk about model-based RL with image observations, or just generally when you have very high dimensional inputs. And this is a scenario that I think actually comes up a fair amount. Oftentimes you can't directly observe some really nice low dimensional state. And so for example, say you want the robot to be able to use the spatula to lift the white object into the bowl. In this case, in general, the robot can access camera images. It can't access the position of the objects directly. And we'd like to be able to we'd like to be able to solve this task with model-based RL with only access to images. Also, it's difficult to define a reward function with only observations. One thing that we could do is learn the classifier, like we talked about before. But in other cases, maybe we might not want to learn a classifier because maybe it would take a fair amount of supervision. So for the reward signal, one option is to learn a classifier. Another option is just to try to provide an image of the goal of what you want the robot to solve. And then this essentially corresponds to goal conditioned RL. So you could give it an image that looks like this and say, I want you to try to reach this image. And you could use this to try to derive some reward function that tries to match images, for example. Okay, so in terms of approaches for this problem setting, there's three classes of approaches. One is to learn a latent space and learn a model in that latent space. The second is to learn a model directly on observations. And the third is to try to predict alternative quantities rather than predicting future states. So first, let's talk about learning models in latent space. So really the key idea here is instead of trying to model in the original image space, we want to learn a lower dimensional representation of images and then learn a model in that lower dimensional space. So for example, if you have a graphical model that looks like this, where your observations are being observed, but you can't observe your low dimensional states, then what you could try to do is learn a model G that can estimate your latent states from your observation. And so the key idea is to essentially just try to learn this latent encoder G. And then once you get this latent dimensional state space, then you can just do model-based RL in that space. There are a couple different approaches that have looked at a problem like this. And we'll go over essentially these two approaches. Really the key challenge is actually how do you do this first step of learning the latent, the low dimensional latent state space. Okay, so in terms of the high level sketch of the algorithm, first we'll collect some data. Then we're going to learn the embedding of your observations, as well as a model in that latent space. And then we'll use this model to optimize for actions. And then we can execute the actions and potentially iterate this process. So this is the same algorithm as before. It's just the first part of step 2 has changed to also learn this latent embedding space. Now, what is the reward function for optimizing actions? One thing that we can do is if we have an image of the goal, we can use the negative distance between the embedding of the goal and the embedding of your current observation. And this can give you a reward signal that assumes that distance in your latent space is a reasonable metric for measuring distances between states. Cool. Now the key question is then, how do you optimize this latent embedding? One approach, I guess I don't want to go into too much detail here, but one approach is to essentially learn something that looks like a lot like a variational autoencoder to learn a latent space. And in particular, you'll try to learn a latent space that can reconstruct your images. This approach is slightly more sophisticated than that. Instead of just learning a VAE for a single time step, it's also going to jointly learn that with a dynamics model in your latent space. And this should produce a latent space that not only captures information about the image, but also allows you to learn how to predict in that space. And this makes sense because if you only learned an autoencoder and then tried to predict, it could be that the latent space is organized in a way that's difficult to predict the next state from the current state. Cool. And so kind of as an example of what this does, you can give it a goal state of reaching a particular image shown here. And then once you have your latent state space, you can run planning in that space to try to learn how to reach that goal. And so the left is showing the image from actually rolling out the planning process. And here's another goal state. And then the right is showing the generated predictions from predicting forward one step and then reconstructing the frame by passing it through the decoder of the autoencoder. One thing that's cool about this approach is that it's quite efficient, even though it's trying to learn skills directly from pixel observations here. And so it's learned this behavior with just about 300 trials, which would correspond to probably about 25 minutes of real time. And it's also able to solve multiple different goals rather than just a single goal. Cool. And then as one more example, instead of trying to use an autoencoder, I guess it's still going to be using an autoencoder, but instead of trying to just like kind of only give it the structure of predicting the next state, we can also impose some sort of regularization on our latent state as well. And in particular, in an example like robotics, we might want our latent state space to correspond to positions of objects. And if we want to do that, what we can do is we can pass our image through an encoder and then constrain our latent space to correspond to 2D feature points in the image. And the way that this can work is that you take your last convolutional map, then you take a softmax over the spatial dimension of that map. So then you're going to get a probability distribution for each channel of your conv3 map. And then once you get this distribution over 2D positions, then you can essentially take an expectation, which will take the expected xy coordinate or expected ij coordinate, which looks something like this, which will take that distribution over 2D positions and give you a single point out. It's going to essentially give you the mean xy position for that particular distribution. You can essentially think of this as a spatial attention, where it's essentially attending to the part of the feature map that has high activations. And the result of this is that you'll get each 2 dimensions of your latent space are going to correspond to a 2D coordinate in your image. And you can then actually overlay those 2D coordinates back on the image itself. And here are 2 examples of feature points that this kind of autoencoder will give you. And you can see that this is visualizing the feature point over time. And you can see that one of them is tracking the finger of the gripper, and the other one is tracking the object. Cool. And so essentially the embedding here is much more structured than if you were to just have a more unconstrained autoencoder. Cool. And then if you use a latent space like this and run model-based RL with this latent space, this is what the kind of learning process looks like. It was initialized with a policy that generally knows how to move its arm to the right position, but not the object. And then over time, it's learning to improve its model and learning how to eventually get a behavior that can successfully push the block over to the left. This was given a goal image of pushing it to a particular position. And then in terms of the final policy, it looks something like this, where it's able to push it to kind of about the correct position on this mat. And then if we go back to the task that we wanted to do before, where we needed to lift the object and place it into the bowl, I can also use this sort of model-based RL approach in the latent space in order to solve the task. And then lastly, you can also visualize the feature points on top of the image, which is kind of cool, and see what kinds of representations it's learning. And we see that in each of these cases, it typically learns at least one feature point that tracks the relevant object and other feature points that track the arm or track other parts of the scene. Cool. And so this was looking at 3 different tasks. And for each of these tasks, it was learned using about 11 minutes of robot time. So this is, again, emphasizing that model-based RL approaches are pretty efficient. Yeah, and the caveat here is that the representation was actually learned also in a fairly environment-specific way. Cool. So that was one approach, which is to try to learn a latent space that, and then run planning in that latent space. Now, in both approaches, we're learning this latent space by reconstructing the image. And the first approach reconstructed the image and also learned a dynamics model in that latent space. Now, a thought exercise for you is, why do we need to reconstruct the image? And in particular, could we learn an embedding space, learn a representation space, and the encoder for that representation, such that you're able to predict the next representation of that encoder? Any thoughts on whether we could do something like this? And to be clear, the objective would be that we have some encoder G that tells us, that encodes our observation, and we're going to be trying to kind of optimize for the parameters of G with respect to the ability to predict ST plus 1. So we're learning, I guess this would be both with respect to G and with respect to F. Does anyone have any thoughts on whether you could do something like this? Yeah?
So if I construct anything that's sort of regular, I think the embedding into that and everything that your embedding society actually separates the different observations from the instance.
Yeah, so when you also include an objective that tries to reconstruct the observation, you're essentially you're saying that we are regularizing the embedding to separate out different observations. Yeah, any additional thoughts on that? Any thoughts on, I guess, what do you think would happen if, what G would you get if you optimized this objective? Yeah?
Could probably just collapse.
Yeah, so what could happen is if you optimize this objective, the representation could just collapse, because what it could do is it could learn to map G, for example. G could just learn to always output 0. And if you always output 0, then you can perfectly predict this objective because it's always 0, right? It doesn't have to be 0. It could always output 5 or something. And then this model just knows that I should always output 5. And then you get 0 lost here. And life is good in terms of this objective, but life is not good in terms of actually being able to use this embedding for performing tasks. Does that make sense? Cool. So kind of the takeaway here is that we can't just try to optimize for predictability in some latent space. We also need that latent space to reconstruct parts of the observation, or somehow it needs to be told that it needs to encode information about the observation. Because this objective isn't, there's nothing in this objective that tells it that S needs to encode anything about O. Cool. So the benefits of these approaches that learn in a latent space is that they are able to learn pretty complex skills fairly efficiently. If you use a structured representation space, then this enables pretty effective learning. The downsides are that the reconstruction objectives might not recover the right representation. And we kind of talked about before how there was a question that came up that, like, if your state has a lot of stuff in it that isn't relevant to the task, then the model might choose not to model the stuff that's relevant to the task. And as kind of an explicit illustration of this, at one point when I was running some of the experiments for the previous paper, I wanted to get the robot to essentially like toss a ping pong ball. And this is an example, like grayscale, low dimensional image from the robot's camera. You can see the ping pong ball in white. And then I tried to train an autoencoder on this data. And what I got was a reconstruction that looks like this. And essentially what you see is that the autoencoder is just deciding to ignore the ping pong ball because it was kind of hard to reconstruct. It's also only a small part of the image. And it doesn't really get that much of a loss incurred by essentially erasing the ping pong ball. And so this means that sometimes these approaches, if there's a large part of the image, a large part of the observation that isn't relevant to the task, and a small part that is relevant to the task, it might choose not to represent the things that are highly relevant to the task. And this can be a big downside. And so essentially we need better representation learning methods, ideally unsupervised representation learning methods, in order to solve this kind of problem. Cool. And then it's also worth mentioning that these, using low-dimensional embeddings can also be useful for model-free approaches, not just for model-based approaches. There's this older work from 2012 that learns a latent space and does fitted Q iteration, which is essentially a variant on Q learning in that latent space. You can also do TRPO, which is a policy gradient method in a latent space on a real robot, and it ends up being much more efficient than if you were to do it on the original space. Low-dimensional embeddings can also be useful for computing rewards. Some works have essentially used a video representation and used an encoding of that representation using something like ImageNet features in order to measure the reward for the task of opening a door. And then you can train a robot to optimize that objective, and it can learn to open a different door, for example, using a reward function in that latent space. Great, and then also if you have reward function labels, then you could also use it to form an even better latent space as well. A lot of the works that we talked about before, we're trying to learn these latent spaces in a more unsupervised way. But in cases where you do have some supervision, you can use that and leverage it to, for example, pay attention to the ping pong ball and encourage it to do that. Great. So the previous class of methods was trying to learn a latent space and learn a model in that space. You can also actually just learn a model in the original observation space as well. So essentially, if you take the MPC algorithm, you can essentially just replace all the S's with O's and just do the same thing as before. In this case, the model needs to directly operate on O. And so this means that you'll need to learn a fairly complex model in order to, for example, predict video into the future. And so as kind of one concrete instantiation of this, we could run a random policy to collect some data, like data that looks like this, then learn a model to try to predict what the future will look like. We can get a model that essentially can predict different futures, different videos into the future based off of the actions that the robot takes. One of the things that's cool about operating on images is that you can also apply these images, these models to things like deformable objects, like towels. It's pretty difficult to think about how to represent the state of the world if it involves a towel. But if you can operate directly on images, then, or learn a latent representation, then that allows you to manipulate deformable objects. And then once you have this video prediction model, you can use it to optimize for action sequences. As a couple details here, in terms of how to predict video, some of the kind of best approaches right now will use a deep recurrent neural network. They'll try to predict multiple frames into the future, and they'll condition that network on actions so that it's actually incorporating the robot's actions into its prediction of the future. And oftentimes these models are stochastic in order to try to capture the uncertainty about what future images will look like. Yeah?
And one quick question to the slide before. If you go back, how do we optimize for the action sequence? So we're given like a goal image of where we want to be, and then.
Yeah, I'll talk about that in like the slide after this one. Yeah. So in terms of predicting video, one other thing that I'll mention for predicting video is that one thing that's pretty cool is if you scale up these models to be larger, you can actually get pretty good predictions. So these are predictions on a deformable object data set. And you can see that the predictions which are shown on the left are actually, I mean, in this case, maybe even indistinguishable from the ground truth. And this means that if you can get very good predictions, then you should be able to plan very well with this model. I'll talk about how to plan, and then I'll talk about how to get rewards. So for how to plan, we can do the same sort of sampling-based optimization that we talked about before. So as an example for like random shooting, this would look like sampling a bunch of different action sequences, such as these two actions, then predicting the future for those actions. And so you can run those actions through your video prediction model to predict different futures. And then pick the future that you like the best and execute the corresponding action. And then you can repeat kind of the steps 1 through 3 to replan like we talked about before. So essentially this is just this MPC approach that we talked about before, but in visual space, or visual MPC. Cool. Actually, I don't actually have a slide on getting rewards, but there's a few different approaches that you can use. One is to learn a classifier. So if you learn an image classifier that tells you if a future is good or not, then you can, when you're kind of evaluating your futures, you can run those predicted images through your image classifier, and it will tell you if a future is good or if a future is bad. Your classifier will need to generalize to predictions from the video prediction model. And so if they're blurry, for example, you'll need to account for that. Another thing that you could do is you could give it a goal image. And if you give it a goal image, then you can just look at like L2 distance or distance in some space between that predicted image and that goal image. One last thing that you can do that's a little bit more complex is you can tell it where you want objects to move in the image. Like tell it like I want this pixel to move over here, for example. And there are some video prediction models that implicitly predict how pixels are going to move in the image. And for those kinds of models, you can actually essentially use their flow predictions to evaluate whether or not it's accomplishing a certain goal. Cool. So as an example of that last approach, you could say, I want you to move this red pixel up to the top left. This would correspond to a task that's kind of roughly along the lines of folding the short. Then you can run planning with respect to that goal, and it's going to say that this prediction looks pretty good in terms of accomplishing this objective. And then you'll run these actions on the robot, and you'll get behavior that looks something like this. Now, one of the things that's cool about this is that you could actually use a single model not just to solve this one task, but lots of different tasks. So you can give it a goal of picking up the stuffed animal on the left. You can give it a goal of moving the sleeve of the shirt over to the right, putting an apple on a plate. And essentially, it's going to use its model to plan to accomplish these different goals at test time. And you don't even need to tell it these tasks during training. Yeah?
Moving in discrete steps.
Yeah, so the question is there a reason why the robot is moving in discrete steps? I guess there's a few different ways to actually do robot control. One is in a more, like a very synchronous fashion where you move, and then you pick an action, and then you move again, and then you pick an action. You could also do it asynchronously. One of the things that's, I guess if you're replanning at every time step, that planning time might take some computation time. And I guess there's a few things here, but one is that if you want to replan every time step for that current image, then it's easiest to do things synchronously. You can, in principle, do it asynchronously, but it gets more complicated. And you also need a control for the frequency at which you collected the data and the frequency that you're actually rolling out the actions at test time. Because you don't want to have a mismatch in your control frequency, because then you'll have like a mismatch in the data distribution. And here are kind of a few more examples of tasks, including the last example of like folding a towel over an object. Cool. So in terms of modeling directly in observation space, one thing that's pretty nice about this is, I guess in comparison to some of the other approaches, this is operating on real images. It also requires pretty little human involvement. Training this video prediction model is like fully self-supervised on your data. And you can also accomplish a lot of different tasks with a single model. The downsides is that if you have a lot of background variability, it's going to be much harder to learn a good model. And this kind of planning approach here can't handle as complex skills as other methods because it's just using like a random shooting planner. And yeah, more sophisticated planners and so forth can accomplish more challenging skills. Also, because the model is so large, you can't roll out that many samples unless you have a ton of compute, basically. So it's fairly compute intensive at test time. Okay, and the last thing I'd like to mention is that instead of predicting future states or future observations, in some cases you can also predict other quantities. And there's a few different kind of instantiations of this. So if you want to learn how to grasp, you could try to predict, like, if I take these actions, will my grasp be successful? Or if I take a sequence of actions, will I collide into something? Or if I take a sequence of actions, like what will my health be, what will my damage be, and so forth. You can essentially think of this as a different variant of model-based RL, whereas instead of predicting the state into the future, you're predicting some statistics about that state. And then you can use the same kinds of planning approaches with these predictive models. This also has a fairly close connection to Q-learning. So if you think about the reward being the probability of some event happening, then these kinds of approaches are predicting the probabilities of events. And so in that case, they're essentially predicting future reward, and Q functions are predicting future reward as well. So the upside of this approach is that you're potentially only predicting these task-relevant quantities. And this can be quite helpful, quite useful when you have very complex observation spaces. The downside is that you need to be able to observe those quantities. You need to have labels of those quantities in your data. And of course, you need to pick the quantities somewhat manually. Great. So to wrap up, we talked about model-based RL in this lecture. And we also talked about model-free learning previously. And so I'd like to illustrate some of the pros and cons of these approaches. For models, it's pretty easy to collect data in a self-supervised way and train the model in the self-supervised way. These models are very transferable across different reward functions. And typically, they require a smaller quantity of reward-supervised data because you're offloading a lot of the effort onto learning the model rather than learning a model of reward. The downside is that these models are optimizing for being able to predict the future and not for task performance. And sometimes it's harder to learn a model than it is to learn a policy. And then lastly, you sometimes need assumptions in order to learn more complex skills because the models for those more complex skills might also be fairly complex. In the model-free case, it makes very little assumptions with regard to like the complexity of your observation space, the complexity of your dynamics, and so forth. And it's fairly effective for learning complex policies. The downside is that it ends up requiring more experience typically, and it's also a harder optimization problem in the multitask setting because you have to learn kind of multiple queue, like you have to learn like a multitask queue function or a multitask policy. Ultimately, I think that we, in many scenarios, probably want elements of both. If we can learn a good model, then we should use that. But it would also be nice to have some of the kind of pros of model-free methods. Great. So that concludes the main content for today. For next time, we've talked about multitask URLs so far, and so next week on Monday and Wednesday, we'll talk about meta-reinforcement learning. And then as a couple of reminders, the mid-quarter survey is out, and homework 3 is out as well.